Before I introduce today's speaker, I want to acknowledge that we are on the traditional lands of the Duwamish people, most of whom are now part of the Muckleshoot Nation. Today, it's my pleasure to introduce Dr. Johnny Seals from Rice University. Johnny is a geoscientist who has worked on many aspects of planetary interiors, both on the Earth and beyond the solar system. He got his PhD at Rice as well, and he is now a postdoc there. And I also want to acknowledge that before this, Johnny was in the military and is a combat veteran who served in Iraq. And so I humbly and profusely thank you for risking your life for the rest of us. So I can't thank you enough for that.
My pleasure.
I also want to say that we will be taking Johnny out for dinner. So if any of you are interested in tagging along tonight, please come find me after the talk. So with that, I think I'll just turn it over to Johnny so he can tell us about all the great research he's been up to. If I get 6 feet away, you can take
All right.
it.
Cool.
Yeah.
All right, thank you for that introduction, Roy. Can everyone see my slides okay? Just a thumbs up, just a yes. I assume everyone in here can. For those I couldn't see, I got plenty of thumbs up, so I'll just go with that from here. Thank you, Miles, for the thumbs up on the actual slide itself. I am Johnny Seals, and today I'm going to discuss with you the maintenance of melting and the role of interior processes for habitability. And I wanted to begin with the slide that we see here, because I thought that it was something that each of us could appreciate. For me, I appreciate it for a few different reasons. One, just I think it's aesthetically beautiful. I think it's amazing that we could actually have this image and that a human itself could take this image. I appreciate it for other reasons as well, in terms of the time scales that it can actually capture. So we can see motions in the atmosphere. We can go outside and experience the wind, and that's something that's very immediate. We can also see on this that there are continents and there's water. And we know that these continents are moving on the surface of the Earth, that they're moving over billions of years, hundreds of millions of years. They're going to open and close new ocean basins. Now, this is something that I'm interested in, is how they open and close. And I'm interested in these geologic timescales. Now, the other thing that interests me about this image is that it happens to be the image of the only habitable planet that we know. If we think about the reasons why this planet is habitable, we come to that there are a few different energy sources that allow it to be so. Now, I'm not going to stand up here and pretend that I'm the expert in this room when it comes to solar processes or some orbital processes, but that is one energy source that matters. Now, the other energy source that matters that's going to allow this planet to be habitable is internal energy. Now, internal energy, you can think about, is the heat that's produced within the inside of the planet due to the decay of radiogenics. This is important because that is going to help determine what the temperature is within inside of the planet. And that's going to evolve through time based on how that energy source is tapped. That's kind of what we're going to focus on today. How do we tap that internal energy source? And what does it actually mean in terms of habitability? Now, the reason that this is important is because how we tap that energy source has a direct connection to habitability, and that's through melting. So that's where I'm going to begin the focus of my talk, is how the maintenance of melting has occurred on the Earth. Before we get to that, let's go into a little bit of detail on how the Earth eliminates heat from its interior. This happens through plate tectonics. For those of you that may not be familiar with plate tectonics, it is taking the Earth and we break it into a bunch of different plates, or it's segmented into many different plates. These plates are rigid and they deform at their boundaries. Now, there's a few different types of boundaries. There's boundaries that are where plates are being created. I've indicated here on these red lines. These are typically mid-ocean ridges. There are other types of boundaries as well. You have convergent boundaries where plates are being destroyed. And then you also have boundaries where plates are sliding past one another. Both of these are indicated together in the black. What I like to do is think about what's going on the inside of the planet. So plate tectonics is a surface manifestation of what we're seeing on the interior. So what do we want to do? Let's take a moment. Let's think about this area of the Earth, and let's think about pulling it out to see what's going on in the interior. So for reference, I've left this image on top with the red lines indicating where plate is being generated, the black lines along the coast where plate is being destroyed or going back into the interior. And we can relate that to the mantle convection process. So the red arrows are indicating where warm material is upwelling within the mantle, and it's melting and creating new plate. As that plate moves away from the spreading center, the plate cools. This plate thickens, and given enough time, it's going to become dense enough that it returns back into the interior of the planet. This is a cycle that occurs and continues. It is these motions that are mantle convection, and plate tectonics is a surface manifestation of it. You may be asking yourself, how is it that the rock, the solid rock beneath us, can float? Well, if you think that you're getting enough, if you're applying enough pressures or enough temperature to it, and it's over a long enough time scale, it can deform ductily. That's the type of deformation that we're speaking about here. Now, what we're primarily interested in terms of mantle convection is how it's going to allow the interior temperature of the planet to change over time. This temperature is going to change based on the balance of the heat produced within the interior and the heat lost from the interior. I alluded to earlier that the temperature, the heat produced within is due to the decay of radiogenics, and the heat loss is through thermal convection, here through plate tectonics or active lid tectonics. We're fortunate that we actually have some idea of how the Earth has cooled over its history. What I'm showing you here are some samples that give insight into how Earth's temperature has evolved over its history. I'm showing you the mantle potential temperature on the vertical axis, and I'm showing you time in billions of years ago on the horizontal axis. So to orient yourself, present day is going to be to the right, and going backwards in Earth's history, moving to the left. The data points that I'm showing to you on this graph are from two different studies, Condi et al. 2016 and Herzberg et al. 2010. These give us the sense that Earth was warmer in its history, and then it cooled towards the present day. Specifically, we see this large cooling gradient in the past 2 billion years. Now, rather than just speak about this, let's put a thermal path on here. This is one that is not exact, but it does match some previous thermal history models, so we can get a sense of the behavior. Let's remove the data for a second and just think to ourselves qualitatively what we would expect about how this temperature evolution would influence melting on the Earth. So early in Earth's history, what we would suspect is that as the planet warmed, you would probably see an increase in melting. Then at around 3 billion years ago, after the temperature reaches its peak and then moves down towards present day temperatures of 1350 degrees C, you would suspect that melting would decline over the Earth's history. Fortunately, some researchers have looked into this question, and what we would suspect would actually be wrong. It would be right towards the beginning. Here I'm showing the apparent mantle melt percentage on the vertical axis. If you think of this also as a melt fraction. So you have a higher melt fraction early in Earth's history. Around 3 billion years ago, you begin to see this decline to about 2 billion years ago. You can linear extrapolate this, and you can see that at some point, you may have actually seen a cessation of melting. However, that's not what occurred. 2 billion years ago, you see that this settles into a quasi-steady state around 10, around 0.1 for a melt fraction. Now, this led us to begin to ask and hypothesize what could be occurring. Fortunately, we understand that melting is not just a function of mantle temperature. We understand that mantle water content matters as well. And it's interesting that that's also the element of a planet that we deem as something being habitable, as having liquid water. So we began to formulate the hypothesis. The hypothesis is that changes in the deep water cycle have allowed for the maintenance of melting. Let's go through the model that we constructed to test this out and see what we found for Earth. So we built coupled water cycling and thermal history models for the Earth. We began first with a thermal history. Now, as I said earlier, the change in temperature with time is just a simple energy balance. It's the amount of heat produced within the interior H minus the amount of heat lost, Q. Now, this heat flow is going to scale with the Rayleigh number raised to a power of beta. The Rayleigh number, for those of you that are not familiar with it, is just a measure of convective vigor. And you see its definition here. Now, if you remember earlier, I'm not sure if I mentioned this, but the primary resistor to plate motions is mantle viscosity. That's going to be this term beta. So the Rayleigh number itself is just a ratio of driving forces to resisting forces. You think primarily buoyancy to mantle viscosity in this case. Now, when it comes to these models and these scalings of relating heat flow to the Rayleigh number, we need to figure out what is this actual value of beta. It's debated, but I can tell you at least that the classical view is that it's around 1/3. And the reason that they arrive at these values is through a number of different methods. One is through theory, as you see on the left side here. This is actually presented within Jeff Davies' textbook. And this is through thermal boundary layer theory. And it goes through and calculates the scaling relationship of heat flow and Rayleigh number based on a critical boundary layer. An alternative way to do this is to set up experiments, as you see in the top right. I actually did these experiments as part of my graduate degree, and I was fortunate enough to do them with my son in Helga Gonerman's lab. Now, these experiments themselves are just a simple tank, and they have some fluid within them. Here it's a viscous fluid. We can use corn syrup, as we did here. You heat the tank from below, you cool it from above. You can measure the heat flow that's coming into the system, and you can calculate what the Rayleigh number is for that tank, and you can get your scaling. You can also do this using numerical simulations, solving the Navier-Stokes equations. Sorry, this isn't showing up very well here in the room, but these are from numerical experiments that take a similar type of box with a viscous fluid in it, heat it from below and actually within as well, and calculate these types of relationships. Now, that's important, but what is also important is that mantle viscosity itself is going to be a function of temperature and water content. And this is going to play into the dynamics. It does so through multiple feedbacks. If you remember that eta in this diagram is going to be mantle viscosity, we can step through this two-sided diagram. On the left side is going to be temperature. On the right side is going to be water content. We can ask ourselves, what's going to happen as we increase temperature? Well, as we increase temperature, it's going to decrease mantle viscosity. As you decrease mantle viscosity, this is going to cause the material to convect more vigorously. As that convects more vigorously, it's going to increase the heat flow, and that's going to reduce the temperature. So you have an overall negative feedback. If we were to also increase that temperature, and we were to think about what it did to water transport, on the water transport side, as you make something hotter, it's going to want to melt more. So you're actually going to take more water out, and you're going to dehydrate the mantle. As you dehydrate the mantle, it's going to stiffen it, which is going to make the convective velocity go down. So I hope that you can see within this, you have competing effects that are ongoing on these two sides. Temperature is wanting it to behave in one way, water is wanting to behave in the other. We have to think about how these two effects are going to influence the cooling of the planet. All right, outside of thermal history, the next thing that we want to consider is water cycling itself. as I've shown you that it does matter. Now, what exactly do I mean by water cycling? Well, there's a certain amount of water within the interior, and there's a certain amount of water at the surface. Over the age of the planet, this is going to change. Water comes back into the interior of the planet from the surface at subduction zones, which are highlighted in this blue box. What's happening is, as the plates are bending, there's cracks that are forming or faults that are forming deep down into the plates. Water is moving along these fractures. It's altering the composition of the rock. And then this water is being bound and carried back into the deep mantle. Simultaneously, we're having melting at the mid-ocean ridges. And so at this location, we're actually losing water from the mantle. We'll go through this in a little bit of detail, but you can think of what is the net balance that's occurring at these two sources. How that's evolving through time is going to determine how the interior water content is going to change through time. And by proxy, how the surface water is going to change through time as well. Now, the last thing that I want to cover within our model is the actual melting aspect. For those of you that are unfamiliar with melting, hopefully I can bring you up to speed rather quickly. What we have on this diagram is temperature on the horizontal axis. And then on the left vertical axis, we have pressure. On the right vertical axis, we have depth. So you're getting deeper as you go down. What this line is showing us, this line is termed the solidus. If you're below this line, a rock is not going to melt. If you're above it, it's going to melt at least in part. Now, if you were to add water to that rock, it would depress the solidus. It would move it to cooler temperatures for the same depth. So that means it's going to melt more easily. Let's remove the dry solidus, and we're just going to focus on the wet solidus for our models. Now, the other aspect that we need to know is that if at the same depth you increase the temperature of that rock, you're going to get to a point where the entire rock itself melts. So this is what we're meaning by melt fraction, is what fraction of the rock is actually melting. And the way that we're going to calculate that is based on the geotherm. And the geotherm itself is composed of two parts. We have a conductive profile at the shallower depths, and then a convective profile at deeper depths. Where the geotherm exceeds the solidus, you're going to have melt. That's this shaded region here. Now, the melt fraction is going to be the ratio of the difference between the geotherm and the solidus and the liquidus and the solidus. I think that's pretty straightforward. The alternative measure that we actually want to track within our models is known as a homologous temperature. So it's going to be the ratio of the geotherm to the solidus itself. And the reason that we're tracking this is it may give us a sense of how these two are moving relative to one another. So the geotherm is going to evolve over time as the planet cools. And as the water content of the mantle evolves over time, the solidus is also going to migrate in temperature space. Now, to tie this all back together, remember that our model has three elements, and we're looking at the hypothesis that changes in the deep water cycle have allowed for the maintenance of melting. Let's step through and actually look at some of our results. This doesn't show up as well on the screen as it does for those of you on the computer. But what we have here are the same data constraints for the Earth that I showed previously. Remember, I stated that they're indicating the Earth has been warmer in its past and cool to its present. So we have a number of models that we're showing here, a number of thermal paths greater than 250 that we're actually using within our analysis. And we ran a total of 10,000 models using these 250 paths. And that's because we would test combinations that related to the Urey ratio and perimeter combinations that related to the Urey ratio and that perimeter beta, which I said was allowed to vary. If you care to know the details about that, you can see me afterwards. So given these mantle temperature constraints, what do we expect for mantle water content? That's what I'm showing you in this figure. On the vertical axis, I'm showing the amount of water within the mantle, and I'm showing it relative to present day ocean masses. So a value of 1 is equivalent to 1 ocean mass at today's surface. We can see that the mean outline, the mean solution that we have here, which is indicated by the dark black line, is decreasing throughout Earth's history until about 2.5 billion years ago, when it goes through a transition and begins to increase. So what's happening? The interior is experiencing a net degassing throughout that time period, and then net regassing begins to occur. We can see that there is some uncertainty associated with these values, which are indicated by the interquartile range in the darker gray, and then the 5th and 95th percentiles in the lighter gray. So how does this actually affect melting? Well, we were able to calculate melt fraction, giving the model that I showed you earlier. We see that early in Earth's history, melt fraction was higher. Our mean solution is that it was somewhere around 0.3. Then it decreased as we went into the future. Rather than continually decline, it actually settled within the past 1 to 1.5 billion years. This isn't quite the 2 billion years that we see in the data or in Keller and Schoen's results, but we are capturing the qualitative trends that we expected to. So this is suggesting to us that the deep water cycle may be playing a role in the maintenance of melting. What about the homologous temperature? Now, if you remember, I introduced this to you earlier, where the homologous temperature was the ratio of the geotherm to the solidus. And this is specifically at the base of the lithosphere. So it's where we transition from that conductive profile to convective profile. What's happening? Well, the homologous temperature is decreasing over time until around 1.5 billion years ago, and then it begins to increase. You may be asking yourself, how is it that you can have a flat melt fraction, but an increasing homologous temperature? The homologous temperature, remember, is telling us how these two are tracking. So what's happening is the solidus is actually outrunning the geotherm towards lower temperatures. So that's what we're actually seeing in these results. Now, this is also interesting because it does relate to the dynamics. As a cooling planet, what you would suspect, if you didn't account for water, is a decrease in the Rayleigh number over time. However, because the mantle viscosity is adjusting both to temperature and water content, what we are actually seeing is a decline in the Rayleigh number over its history until about 2 billion years ago, and then it slightly increases. Overall, we can say that this stays relatively bounded throughout its history. This is why we suggest that mantle convection, in terms of how it's operated on Earth, may be self-regulated, and it's also buffering melt, as we suggested. Now, the question that we may want to ask ourselves in terms of habitability is, should we suspect this for all planets? Something you can ask yourself. I think that the answer is, I don't know, but we can look. Let's think about what may be going on in our own solar system and what the data may be able to tell us. And we can do that because we're fortunate enough to have planets operating in different convective regimes. The Earth is operating in plate tectonics, as we see on the left, whereas Mars is operating in a stagnant lid regime, which we see on the right. If you're unfamiliar with the large-scale differences between these two, plate tectonics has the outer layer recycling back into the interior. So there's two-way cycling going on with water outgassing and then water ingassing. If we think of just the end member limit of stagnant lid, where there is no regassing of the mantle, you're just going to have degassing throughout its history. Now, what I would like to do is use the thermal history of Mars to actually do a similar type of analysis. This is preliminary work that I'm going to go through, and I look forward to any comments that anyone may have. First, let's compare how the temperatures, the interior temperatures of both Earth and Mars have evolved over their histories. I think now I've shown you a few different times how Earth's temperature has evolved. This here is showing the same data that I did before. I put a little bit wider constraints. I just kind of drew a bound about it in the blue. When it comes down to the orange, the data that I'm showing here are from Filiberto 2017. They fit a line to this data that goes down the middle. And I just bounded this with some sense of uncertainty, just to get the qualitative trends that we may be expecting to see. I think it's pretty surprising that you do see some overlap between these two planets. That's especially surprising to me, given that Mars is the smaller of the two planets. If you're interested in why that may be, see me afterwards. We can probably have a discussion about it, or I can point you to my paper from earlier this year. The primary reason for that is because Mars itself could be at a similar temperature today because of its decreased convective cooling efficiency. Now, to take and do the type of analysis that I did in the previous model, in the previous section with the Earth results, I'll take the data constraints on the right, and here I'm just running 3 models, not the full suite. I have not done that full analysis yet, but I can show you the mean solution in orange, and then some bounds about that for the internal temperature. Whereas on the left, what I'm using as another data constraint is the effective elastic thickness. And so this is going to allow us to constrain how the stagnant lid has grown over the planet's history. So let's just get to some of the results, and let's think about how the interior of the planet has had water evolve over its history. Now, when I first saw this, I thought to myself, great, this is actually a good result. We're seeing mantle water content in ppm. The average solution was around 600 ppm. That's not out of bounds with what's been estimated from accretion models. That's good. That's positive results. We like to see that. These mantle water contents are in line with the results of Sandhu and Kiefer in 2012, who ran a Ford model and modeled out gassing rates. And they used constraints on the geodynamo shutdown, or the solidification of Mars core. Now, what I would like to show you, let me not jump ahead of myself. The most important trend that we can see from this data is that Mars began with a higher water content, and over its history, it decreased. This is telling us that the planet degassed over its history. Now, we don't know exactly what happened to this water. We can make an assumption about the ratio of intrusive to extrusive magmatism. What do I mean by this? How much water escaped to the surface? If we assume that approximately 10% escaped, that's using the reference of Lillis et al. In 2009, we get the following for the global equivalent layer. Now, what is the global equivalent layer? The global equivalent layer is if you were to account for the amount of water at the surface and you were to homogeneously distribute it about a radius of that planet, you would get a layer of water of depth, this vertical axis in meters. So you'll see some issues. We have some negative values for the global equivalent layer. One thing that we've assumed here is that there was no water at the surface to begin with. So this is just taking and calculating how much water has been degassed and allowed 10% of it to actually be lost to the surface. We can see that it reaches about 120 meters depth. Also, what I have not done here is allow escape of water to space. So these are our raw results. So in the future, we'll be trying to analyze these more deeply and running a larger suite of models. I'm actually working with Valerie Pyrie at Northern Arizona University, who's taking the internal compositions, the internal water contents and temperatures, and trying to calculate basalt compositions over time. She's seeing some pretty promising results as of now. So the other aspect that we wanted to look at and that I wanted to come to was, can mantle convection on Mars, that mantle convection on Mars does not experience self-regulation. What makes me think this? Well, if we look at its Rayleigh number, it monotonically declines over its history. That's different from the Earth. That's different from what we experience there. And we have some confidence in these Rayleigh numbers, at least preliminarily, because they're matching around 10 to the 6th to 10 to the 7th. That's what Lee and Kiefer found as well. So what do I want you to take away from this part of the talk? Why is it relevant to you as astrobiologists, and why is it important for habitability? Well, I think what's important about it is that, one, plate tectonics is pretty efficient at its cooling. And because it does have deep water cycling, it was able to buffer melting over its most recent few billion years. And we're able to capture that using changes in the deep water cycle. Second, that Mars, or a stagnant lit planet, could degas over its history. So this is suggesting that you can have either tectonic mode and still be habitable. This isn't too controversial of a result, as I think some work in the recent decade has shown this. For instance, Ma and Foley, their work comes to mind, as well as Tosi et al., who showed that stagnant planets could indeed be habitable. Now, what we actually want to do is we want to couple the interior evolutions to calculate surface temperatures. And that's what I'm going to do in this next part of the talk. So when we think about the thermal history, the type of model that we're going to need, we're going to need to understand how the interior temperature evolves over time. So we can take the thermal history module that we had before, and we can relate water outgassing and ingassing. Remember, outgassing is occurring in mid-ocean ridges. Ingassing is occurring at subduction zones. We also would like to know how CO2 in the atmosphere is going to evolve through time. So we can capture that. It's going to evolve based on weathering rates, as well as we need to know what the temperature is of the surface. So we have a climate module that's capturing that. And then this is going to be forced by the other energy source, by solar luminosity, and how that's going to evolve. So taking everything together, we were able to track how the interior evolution evolved, and then estimate surface water content, PCO2, and surface temperature. Let's step through some of those results. These are the same constraints for Earth that I showed you earlier, except this time, what we're doing is being more liberal in the models that we're allowing to work. Each of the models that you see fitting here match within structural uncertainty of that model. So the solution paths that I'm showing you here, one line, is just a mean solution. There's some uncertainty about that mean. And each of these paths can match this data, or allowable within these data constraints. And generally, what we see is that the planet is cooling over its history. So how does this relate to surface water content? Well, that's what I'm showing you here. It's presented in a similar form as it was before. That's in ocean mass equivalents. Here, the values range from 0.95 to 1.35. We can see that early in Earth's history, on the left side of the diagram, goes around 1 ocean mass. As the planet cooled, it outgassed. This created an increase in the amount of water at the surface. And then over time, this changed to where there was a change to net regassing over its history. And then water content came back down. So the amount of water at the surface decreased. We see that this comes somewhat in line with what we'd expect. This actually matches the results that we showed earlier as well. So that gives us some confidence in them. The results that I'm showing you here are the black solid line is a mean of our output. The dashed line is a 1 sigma uncertainty, and the dotted line is 2 sigma uncertainties, just to be clear on that. That'll stay consistent throughout the remainder of these slides. So the next thing that we want to look at, how does PCO2 evolve over time? That's what I'm showing you on the vertical axis here in bar. The red line is indicated present day values. What we notice is that early in Earth's history, PCO2 was higher based on our thermal evolution models and our coupled models than it was today. It was higher by orders of magnitude. And this makes sense conceptually if we think it through. Now, Earth was hotter in the past. That means that it likely had a higher Rayleigh number and was convecting more vigorously, and therefore was outgassing more CO2. So it at least is in line with what we would expect our model results to do. Okay. So the question is, how does this actually affect surface temperatures? Well, that's what I'm going to show you on this diagram. Surface temperatures on the vertical axis. I'm giving it to you in Kelvin. Now, the threshold that I'm showing here is 273. That's for a global surface average temperature of 273 for liquid water to be present. We see that there's 3 different types of behavior. We see that some models, for instance, this dashed line, would stay above this threshold throughout the entirety of the planet's history. other models may begin above the threshold, dip below it, and then come back above. Whereas some models will start below this threshold and then rise above it. Now, we know for the Earth that water has been on the Earth for billions of years. So we know what the Earth has actually had and experienced. But these paths are Earth-like in the sense that they do match the thermal history constraints of the Earth. So it does not mean that we can roll out these types of behaviors. Another way to visualize this is using a cumulative probability distribution. We're calculating the cumulative probability of that distribution. So what this is saying is, what is the cumulative probability that one of the planets had a surface temperature that was above that threshold of 273 Kelvin? So as I said, we had those planets that first remained over the threshold over its entirety. So that's why we begin around 0.1 and it stays that way for some time. And then the most recent, then around 3 billion years ago, we have some planets enter into the habitable zone. So cross this threshold. And then that continues until about 1 billion years ago when the last of the planets come past that threshold. So what is this actually trying to tell us? This is telling us that for the Earth's data, when you rise above this threshold, when you enter into the habitable zone, could span billions of years. There's a large uncertainty in that actual number of when that entry point could actually occur for an Earth-like planet as we have described it here. Now, what's the value of this? Well, we can take and we can calculate this at different orbital distances. We can then plot the cumulative probability as a function of orbital distance. Here we can see, as we would suspect, right, as you move in closer to a star, you would be more likely to be above that threshold the closer in you are to the star. I will make the point that I'm not calculating when you would be above some some runaway greenhouse in these models. Let's just be perfectly clear about that. This is just when you'd be above 273 Kelvin. In the future, that is what I would like to do, because I think those would be the probabilities that we're after. So you could calculate this for all of these different orbital distances, and then you could ask yourself, what if we wanted to be above that threshold for 4 billion years? Then you can assign some confidence that you had, and you could identify, okay, I needed to be at this orbital distance or closer. This is one way that we could employ the thermal history models of Earth. You could also do that for a number of different time windows as well. Now, what I would like to do is close with perhaps some thermal history models that may be a little bit different. These are not as constrained, and these are considering when we may have larger internal fluctuations within the cooling history of a planet. And everything else is going to be the same within our coupled model, except our thermal history module is going to change. And the thermal history module that we're implementing is actually Jeff Davies from 1995, and it's punctuated tectonics. And it actually allows for these catastrophic overturns. So these could be interesting in terms of how a planet may evolve. Just to give you a sense of what the models may look like. Here I'm showing you mantle temperature as it evolves through time. The orange lines are going to indicate lower mantle temperature. The blue lines indicate upper mantle temperature. And so what's happening is that given enough time, you're experiencing these catastrophic overturns where you get an inversion of temperatures. So this happens at a periodic, at some frequency. And what we can do is evaluate how this influences the atmospheric composition of CO2. So what we end up seeing is that you have spikes of CO2, which is going to manifest in spikes of surface temperature. However, what we're assuming also is that there is enough weathering potential to draw down that CO2. So you have some background outgassing rate a large burst, and then you return back down to that outgassing rate. We're assuming within these models that you have enough weathering potential to draw down that atmospheric CO2. What becomes interesting is what would occur if you didn't have that weathering potential. In the case that we have here, we can think of how surface temperature would evolve over time if we just allowed a common background noise of outgassing throughout its history, and then allowed for weathering to be in steady state with that. Surface temperature wouldn't change over time. Now, if we were to allow for outgassing rates to be held constant, but not necessarily have the weathering capacity to draw down all that CO2, you would have an increase in temperature with time. What becomes interesting though is if you impose on that these types of pulses. So for instance, you have a pulse and then weathering draws it down. This ends up being in some perfect equilibrium. However, you can get a ratcheting effect, which I believe was coined by Matt Weller. You have a pulse of CO2, and then you have some weathering that occurs, a pulse of CO2 outgas, and then some weathering. So this could drive a surface temperature climb, the surface temperature of a planet up towards a runaway greenhouse, given enough time. All right. So what I would like you to take away from my talk today is twofold. First, I'd like you to take away that deep water cycling and melt buffering are connected on plate tectonic planets. And I hope that I showed that to you using our coupled models today. It's also important to remember that what is connecting the interior evolution with the surface is melting. And I showed to you that that melting could be sustained on Earth. However, on Mars, we can't rule out that there has been loss of water from its interior, which perhaps could be inferred that there's been melting over its lifetime. And then when it comes to coupling the interior to the surface, hope you take away that there's an extended window over which a planet may enter the habitable zone based on the different allowable tectonic variations. Thank you.
Thank you very much, Johnny. We have time for questions.
Uh-oh. Sure. We'll go in the back and then to the front.
Okay, cool. Did you calculate hydrogen outgassing on Mars?
I did not.
Are you going to do that, or do you think that's?
I think that that's something that I'm probably going to be interested in moving forward. Yes.
So when we look at the geology of Mars, it's the evidence for liquid water on the surface of early Mars, and then today Mars is very dry. But your outgassing history is the opposite. You start with hardly any water and then you get a lot at the end if you just accumulate. So doesn't there need to be a lot of outgassing early on to match what we see in the geology? What do you think about that?
Can you repeat the question too for people online?
Yeah, for people online, I believe if I summarize the question correctly, there's a lot of evidence for water early on in Mars history. And what I'm showing here is not much water in early Mars history. Would that be a fair characterization of it?
Yeah, how do you reconcile those two things?
Yeah, I think one way to reconcile that is that we don't know the ratio of intrusive to extrusive magmatism would be one. Here I've allowed for only 10%. So if you were to go back to those results. So at 4 billion years ago, you could have upwards of 200 meters. If you had all of the water outgas, you could have 200-meter depth global equivalent layer.
But how would that happen then? Just you have a lot of exclusive.
Yeah. So what I've assumed here is that 10% of the water loss is lost to the atmosphere within the results that I'm showing here. If you allow for all of that water to escape, then it would be 10 times greater, is what I was suggesting.
Then my second question is about Earth. Normally, when we think of the climate on million-year timescales,
Mhm,
we think about the carbonate silicate cycle as
Mhm.
being the thing that moderates,
mhm,
which has a feedback through the temperature,
I agree.
CO2 dependence of continental weather, and the temperature, pH dependence of seafloor level.
Mhm.
And I wasn't sure what you did. You said you had some climate thing, and did you actually have a carbonate silicate cycle?
Sure. So the model that I actually used in here was from Walker in 1981, both for calculating CO2 and for calculating surface temperature. Now, we've actually compared our outputs to results from the Lemur 2021 paper and found that our isotherms for within PCO2 and normalized solar flux within actually correlate very well with those isotherms. And the CO2 content that we get within the models that we have here actually overlay parts of that, the findings within that paper as well.
It does look like you were somewhat code
Mhm.
when you get towards the Archaea.
Mm.
But
Yeah, it gave us.
depends on the fine tuning of what you put in your parameters
I
and
agree.
exponential powers and things like that.
Yeah, and so we varied those powers as well. We did an uncertainty analysis on the model as well. The largest uncertainties actually came from the interior forcing rather than from the weathering itself. So we're pretty confident in that, and it gave us confidence that we're actually getting similar results as that paper. So it was good to see.
Okay, thanks.
Yeah, I hope that answered your question.
Yeah.
Okay, thank you. Yes,
Yeah, you mentioned the Uri ratio,
sure.
and I was thinking about extreme cases of variation of the Uri ratio, which is kind of interesting. I think of the oldest stars that formed during the peak of star formation, history of the galaxy, they had actually a high ratio when they formed because it's great depth of thorium that produces very abundance then. But now those stars are really old, and so the Uri ratio is probably 0.1 now.
Yes.
It must have been much higher, so it was higher than we are early on in their history. But then they've gone through this long-term evolution where they've gone through.
So what was?
So how does this affect habitability?
Yeah. So how does
Can
this?
you repeat the question?
Yeah, so the question, if I gather it correctly, to say it succinctly, was how does the Uri ratio affect habitability? Given that,
Especially for stars that formed 9 or 10 billion years ago. But the peak, because then it was high,
Mhm,
but those stars are still here, and you know, their planets are still there,
mhm,
and they must be really low now
mhm.
because it's so old.
Yeah, so I think that, so the question was how given that there are older stars, what is the Uri ratio going to do and how's that going to affect the results? Are you getting at the radiogenic concentrations are going to be lower now to begin with, and so our internal heat source is going to be lower?
Yeah, they were formed
Mhm.
at that time when the supernova rate was high.
Yes.
So their initial radioactive thorium was higher. But now that they're old, they really decay. So your ratio has changed a lot during the lifetime of the planets.
Yeah, and so.
Compared to Earth.
Okay, I think that would be kind of a sensitivity analysis that we'd have to do within our models, is looking at the variability of radiogenic content and its effect on our results. What we did here was use the present day Uri ratio as a constraint. So for the Earth, that varies between 0.2 and 0.5. And so we only allowed models that match that constraint within the Earth section. Yes, we'll go 1, 2, 3.
So I find the self-factorizations ideas really interesting, and I'm thinking about to what extent it can be applied to other parameters like Planetary. And then my question is there some kind of personal or some critical number for say, the amount of water you need on the planet, or some heat source you need on the planet to kickstart the effect process? Or is it like something really specific to the Earth and only on the planet that's really similar to the Earth?
So the question here within the room was, what is there a certain amount of water within the interior of a planet that would cause the dominant feedback of water? You can do an analysis actually. Crowley 2011 formalized an analysis that looks at the relative contribution of the change in temperature and its effect on mantle viscosity to the change in viscosity and its and the change in water content and its effect on viscosity. So you can see you would be able to calculate for which temperatures you would be in a water dominated regime versus a temperature dominated regime, if that begins to answer your question. In terms of how exactly, I can imagine a number of ways that you could get a self-regulating feedbacks. It's going to come down to just balances of cycling.
Hi, so my question is a little bit more about how well your model matches with observed constraints for Earth. So the PCO concentrations that you calculated for Earth, how well does that agree with ones calculated from like delta carbon 13?
Oh. So I didn't.
Can you repeat the question?
Yes. Thank you, Rory. The question was, how well do my modeling results reflect carbon isotope signatures? We didn't model any carbon isotope signatures in this model. I have done that in previous work, and that's an interesting topic, but I didn't look at that in this model.
And but your concentrations that you calculate, like how well do they match up with the ones that we have extrapolated?
So the red line is present day. The black is the mean. 0 is present day. So the mean is pretty close. Does that answer your question?
I think so.
Okay, we can talk about it afterwards and I can clarify. It's probably on my part, not yours. Thank you. And then I think Rudy had a question.
What role does the crustal thickness play in sort of changing that homologous temperature? And does that like play a large role in the sort of like melt buffering that you're talking about? And then if it does, or if it doesn't, how does that dynamic change between like a tectonic plate and stagnant plate planet?
Thank you. So I believe the question was, what is the role of lithospheric thickness on a plate tectonic planet when it comes to what we define as the homologous temperature? I believe that was one part of the question. So we did allow for a self-consistent evolution of the homologous of lithospheric thickness here, right? So we're calculating an average internal temperature, and then we're converting that into a geotherm. And then from that, we're able to have a geotherm that has a conductive profile and a convective profile. And so where those two are intersecting is going to be our lithosphere. And so it is evolving over time, and it's actually the thickness of that lithosphere that's going to determine what the homologous temperature is, because that's going to be the last point to cross that solidus. So it does play an important role, if that answers your question. In terms of how it plays a role in a stagnant lid planet, I would have to think about that. I haven't given it a whole lot of thought at this point.
Are there any, well, I would just check if there's any questions online first, and then we can get back to you, David.
Someone didn't hear any sound yet, so hopefully they got that resolved. I apologize, Eric. I hope you got to hear the talk. If you didn't, I believe it was recorded. And my apologies. It was
Yeah.
probably on my end.
Probably would have said something before too.
Yeah.
Okay, yeah, go ahead, David.
Yeah.
So I think one of your earlier plots plotted mantle water.
Yep.
I guess my question is, what Did you look at how much surface water there is in terms of depth of ocean through time? How did that vary in your models, and what's the sort of range?
You know, I should have put that in here, and I apologize that I didn't, and I can send it to you at some point. I did. It ranges from about 1 ocean mass to, I believe, with a like largest uncertainty bound. Don't quote me on this, but I believe it was around 3 ocean mass. 3.
3, okay.
3. Does that answer?
And the 3 would be back at.
Yeah. So it always went, I mean, if we think about, I should state how I calculated that as well. All right, so I assumed that we have a present day ocean mass of 1. And then within these calculations, because they're more of a data assimilation method, I required a mass conservation. So any models that ended up putting negative water at the surface, of course, I cast those out. Those are on physical results. So going backwards in time, I'm not accounting for any loss of water or anything else. And so I just used the basically defined my system water content by taking the present day mantle water content, adding to 1, and then subtracting away the mantle water content throughout history, which will give you a curve for the surface water. And so you can imagine that overall what's happening is it's decreasing over the past 2.5 billion years, surface water that is, whereas you may get some increase as the mantle was outgassing. So it's going to be the inverse of this, right? So you should have an increase in mantle water content up to about 2.5 billion years ago, and then a decrease towards present day. And I believe those values varied from, it stayed constant at about 1 throughout its history and ranged to about, I think 3 was the maximum in terms of the uncertainty bound. The average was somewhere around like, began at 1.25, peaked at around 1.5, and then the largest gradient was closer to present day. As you would suspect if you look at the gradient in this plot.
So it's not a deep range, it's almost like your regular, has some regulation to it.
That's right.
One more question.
So you might have, what you just explained is my answer to this.
Okay.
How did what determined the initial conditions? For example, how much water was in it?
Yeah, so that is self-consistently calculated. This isn't a forward model. This is an inversion for mantle water content.
All right, great. Thank you very much, Dennis. Thank
Cool.
you again.